Measures of central tendency like the mean and median are very useful for studying large data sets. In this video, you'll learn about the mean in the context of normally distributed data sets. Let's start with an example. The batting averages for all National League players in 2019 are shown in this histogram. Assume the data is normally distributed. Estimate the mean batting average. The batting averages range across a number of percentages. At either extreme are players who had low batting averages and some who had exceptional batting averages. In the middle, we find the largest number of batters. This histogram is known as a probability distribution. For any random player, the probability is higher that his batting average will be in this cluster. The shape of this histogram is similar to that of a normal distribution. In statistics, a normal distribution, sometimes referred to as a bell curve, shows the distribution of measurements of a given statistic. A normal distribution shows the measurements cluster in the middle, with fewer at the extremes. For this data set, the mean, symbolized by the Greek letter mu, is 0.252. Because batting averages are normally distributed, the mean is in the middle of the distribution. Let's look at another example. Height measurements are normally distributed. For adult males, the mean height is 70 inches, and the standard deviation is 4 inches. What is the probability that a randomly chosen male has a height greater than 74 inches? For height to be normally distributed means that some men are short and their heights make up this end of the normal distribution, while other men are very tall and their heights are represented here. However, most of the heights of men are found in the middle part of the normal distribution. The mean height is 70 inches and is in the middle of the graph. The standard deviation, indicated by the Greek letter sigma, is a measure of how much a measure differs from the mean. In fact, the part of the normal distribution that is one standard deviation from the mean on either side of the graph accounts for 68% of the data. This means that if you picked an adult male at random, there is a 68% probability that his height will be between 66 and 74 inches. The remaining 32% probability is split across the two outer extremes of data. This means that the probability that a random male has a height greater than 7.4 inches is 16%. Let's look at a final example. Shoe sizes are normally distributed. The average for women's shoes is 8, with a standard deviation of 1.5. What is the probability that for a random woman she wears a shoe size smaller than 5? You can see from the graph that it has the normal distribution shape. A normal distribution overlays the histogram here. We're told that the mean is 8 and the standard deviation is 1.5. For someone to be wearing shoe size 5 or smaller means someone whose shoe size is 2 standard deviations from the mean. The area under the normal distribution that is 2 standard deviations from the mean accounts for 95% of the data. The remaining percentage, 5%, is split across the two ends of the normal distribution. This means that a random woman having a shoe size smaller than 5 is 2.5%.